Hey, we're going to do a quick presentation overview of the decision tree I made here. I did this in R, and we have three files here. This is the training decision tree. This is just a function called best path that finds the best possible path for this car data. And then this is the test of the decision tree. We found several best paths and we tested them down here. So first thing we do here, we need to definitely source our function best path. This function best path, we can only use it in the training. We don't want to use it in the testing. And then of course we load our training data. And I renamed the columns to what I think their actual names are supposed to be. Because I noticed they didn't have their actual names. We did some data changing. So for example, 5 or more, we changed to 5. Same thing with persons, we changed to 5. We made that numeric, those column vectors. And we changed the row for acceptable and non-acceptable, which is, I guess, the final test, to trues and falses instead of having to. We would have to use this kind of snippet right here several times if we didn't just change it to true and false Boolean type values in that column vector for acceptable. So the first thing we do here is, okay, the first thing we wanted to do actually, and I'll show you, is we're going to go ahead and run this. And we're trying to do a quick overview, so we won't go through exactly everything. But first thing I did is I didn't really look up anything on decision trees for this exercise, so it was a good challenge for me to kind of come up with my own method for this, although I'm sure there's a bunch of literature on here. But the first area of attack I thought to do was kind of look at the probabilities of everything. So for example, we see right here that when buying is medium, and so I've just run, this is kind of like a general overview to find some areas of what I call attack for this decision tree, some areas of focus. So for example, if the buying is medium, there's a 70% chance that it will be acceptable. So that's, actually no, let me rephrase that a bit. Yeah, actually that's true. And so you might think, okay, so we want to look for all the high numbers in here. So I did several tests. As you can see here, we're checking buying high, maintenance very high, lug, all this stuff. And then for these numeric ones, we use our for loops. But you might think we're just going to look for the high ones. Actually, the best things are anything that deviate from homogeneous kind of data, or 0.5. So 0.5 is homogeneous. Anything significantly above 0.5 approaching 1, and anything significantly below 0.5 approaching 0 is going to be important. So actually this is a very important thing here, because if we reverse this, if we say buying does not equal very high, then we have 86% right there, or almost. So we go through and I identified some areas of attack. Of course, the buying, very high and medium. We have some oddities here. It's not just anything above, but interesting. Second thing, if the maintenance is low, a little bit, the lower the maintenance, the better in general, but also maintenance not very high as we'd expect. Even better, actually, very high maintenance perform the poorest, on most radically away from 0.5 in all of this. And then we go down here. Yep, we also see a big lug bolt, a little bit better. Try to go through this quickly. Safety, so safety high, definitely a little bit better. Safety low, more important, a little bit worse. So safety not low, something we'd want to check. And so this is something that's important here. We see that doors don't seem to matter too much. All of these are near 0.5, so this is very homogeneous, with 4 doors being slightly better. So this is equals, so exactly that over. Then we checked less than, so, or greater than 1 door, greater than 2 doors, and greater than 3 doors down here. And also did that right here, but most of these are near 0.5, so we're not really interested in doors that much. Now persons we are interested in. So when it was exactly equal to 4 persons, there was a good amount higher. Oh, well, look at here. Maybe we should test that. I didn't notice this earlier. So it looks like 2 doors is pretty bad. So maybe not 2 doors is something we should have tested in my decision tree. So that's actually something I neglected. I'd be curious to do that real quick. So greater, we see greater than, let's see here, greater than 2 doors, so 3 or higher is performing very well. And then less than, we also see some interesting things. Okay, so we get a general idea of some areas to focus on, and so I'm going to start my best path on these kind of paths that perform very highly or lowly. We can just reverse, like I said, we can do it not equal. So we found some areas of attack for my best path algorithm, and we plugged this in. Check my time here. Okay, we plugged this in. So the first thing I tried was buying equals medium. Second test I did was persons greater than 2, and these are all like kind of things that deviate from a homogeneous. 0.5 is something we don't want to test, or doesn't really matter. It's not affecting anything. Then we tested safety equals high. You remember people wanted safety equals high. We also tested buying equals high, safety equals not low, and buying equals very not very high is another thing we did. So let's quickly do that test actually that I was kind of interested in that I realized I forgot, or I didn't notice it earlier. Where is that? Okay, so not equal to 2. So we're going to try persons not equal to 2. So now we'll do a live test. I wasn't planning this, but so is that persons? Yep. Persons not equal to 2. This will be our 7th test down the little node tree. Don't really need to be changing these. This is I didn't have to put an index for these, I realized, but it's okay. So we'll actually test that right now. Let me make sure everything's okay here. So once again, so when persons is not equal to this, looks like it's going to be a pretty high number, almost. One of our more interesting areas of focus. 0.3. Also a little interesting. We already tested that though. So now we're going to run the whole thing. So the best paths for all those tests ran, but let's see the most recent one's going to show up right here. So what the algorithm does, we get a scroll to where it started. So this is our one where we were testing first person is not equal to 2. It's going to go through and it's going to find accuracies for everything against that first value. So it'll take a while to explain, but it looks for anything that would have been a better path after that. So greater than the probability in here. Basically, it's finding the max of these. And we'll scroll down and kind of see what it found. So it found safety is low. So the probability for not equals 2 persons was this right here, 7.7, 70%. And it found it was better to go, if we were to choose the next path, is to check low, safety low. It likes not safety low. Actually, these are nots. I did the opposite of yeses. You know, it would have been better to test the opposite way too, interestingly, which I didn't do. So safety not low actually is what this is. So if safety is not low, it sees some better performance for this tree. And then it goes down further and it sees no better performance than 0.76. So that's going to end right there. So what we did was we formed a tree here starting with not equal to 2 persons, and then safety safety not low, and we can see some other tree paths here we'll go through. So I found those areas of focus and I tested each of them. Like for example, this one only had one path, not very good, but this one right here had two paths, and this one right here had three. Let's see what this one is. So when buying is equal to high, we found that if we go next down to buying is not equal to medium, we get a better result, and then we get all the way up to this, and buying is not equal to low. So we have some weird things with buying low, medium, and high, which I think is causing a lot of problems actually with this decision tree, because actually checking the test data later, we'll see something funny. I'll mention it again. So something's interesting with the test data that makes the training data as kind of liking this for this buying. It often, these paths that I noticed for this data would go down, would be checking buying medium, buying high, and buying low. That seemed to be what a lot of paths really liked. For example, safety. Here's one that was a good one to test. Safety high, because we know safety equals high. And then next it found actually safety medium, also to include in there with a slight improvement. And then what is the last thing we found here? Persons equals to 2. Interesting, right? So that was the best path for that one. So let's go into our, so after we did all these tests, what we did was we plugged into these paths and test decision tree. So each of the paths that were formed down here, I manually put them in right here. You could definitely write something that writes this for you, which would be interesting. But let's see here. So same kind of thing in this test file. We're loading the data, except with the test data. The beginning's the same. We're kind of refining some of our data, changing some of it to numeric only, and making the acceptable true or false. And ACC is true, by the way. The other one is unacceptable. It's like UN ACC, which, of course, anything else is going to be false. That's only two options. So we test each of these paths. So, for example, there were 3 nodes in this test. Remember, these paths were formed based on the best path algorithm. So now we're testing them. So there were 3 nodes in this first test, 2 nodes in the second, 3 in the third, and all the way down. And so we performed 7 tests based on some. So remember those initial areas of focus. We formed a path for each of them using best path. We found 7 areas of focus, and now we're testing to see which one was the best actually. And this is just a funny test I did, and it kind of highlights some of the problem in this data. I think I'll show you in a second, but let's go ahead and run this whole thing. All right, so here's the results here. So anything radically above or below is interesting, but in this case we can't use the things radically below because that is not what we tested for. That's not what our tree forms. So actually, very bad performance here. So our best performance was here, and we'll examine those. This is just a funny one. This is 100% perfection, which would be an overfit kind of, and I'll show you that one in just a second. This is the funny thing I was referring to. So I think a lot of the problem is, like I said, there wasn't. So these ones right here are very good. A lot of the times the paths went down the buying area, because that had some radically low and high things in the test data, but or in the training data. But in the test data, actually, if we look, let's see here. If we go into the test data, we just loaded it. We'll see that actually something weird kind of happens. This test data only has high and low. So I think it's actually kind of some bad test data. In the training data, there is very high, medium, low. This one actually has 100% accuracy for anything that's low is automatically going to be true. So you can actually get 100%. Well, you shouldn't be able to predict it because the training data is different. But this is what this test is. If your tree involves checking if buying equals low, then you'll actually be 100% accurate on this test data. So I think it's some kind of flawed test data for 2 reasons, because of that, but also mainly because it doesn't include medium buying types and very high buying types, which affected the training data a lot. Okay, so our best paths actually, so this one's our real best one. That's that 1.1 here. If buying is equal to low, you'll see it's always true. Look, low, true, low, true, low, true, low, true, low, low, true, true. And of course, everything with high false. Low, 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 true. And so we're going to wrap it up here. I'm just going to show you these two best paths. Our best accuracy was 73%. Best accuracy, 73%. I think the test data was not super good here. And we're going to look at our best paths here. Number 2, test 2, which was the path was first testing persons greater than 2, and then safety equals low. I'm not going to explain the best path because then this video is going to be a little too long. Let's go through it quickly. It's a recursive function basically, and this is the recursive part here. So it's doing all these tests, and if it found something better, it's going to recursively go to another best path test and keep looking for the best path. So this one, so persons greater than 2 and safety not equal low, performed well. Performing equally as well as number 6, which is safety is not low, and well, lo and behold, person equals 2. So that's the best accuracy. So it's noteworthy this sample was smaller. I don't think it was good test data. Another reason because it was smaller. It only had 150 samples. The training data had many, many more. And then mainly this high-low thing, which caused a lot of best paths to the best path algorithm. I really like to give priority to those because those were so radical. And that's everything. Thank you for checking out my little algorithm, and the source code will definitely be included.